In this video, we're going to talk about very simple and basic lengths and dot products in the context of linear algebra. First of all, let's define what a dot product is. So the dot product, or inner product, is for 2D vectors. So vectors with two components is defined to be v dot w. And because v has two components, let's denote it as this. This is equal to v1 times w1 plus v2 times w2. So it's the sum of the multiplication of components. So for example, if we have the vector v is equal to 4, 2, and w is equal to 1, 3, or 1, negative 3 to spice it up a little bit, then what we have here is v dotted with w is equal to 4 times 1 plus 2 times negative 3. And that's equal to 4 minus 6, which is equal to negative 2. So that's all you have to do to compute the dot product. Very simple. Now, consider these two vectors. Consider the vector v is equal to 4, 2 again, but now w is equal to negative 1, 2. The dot product of these two vectors is 4 times negative 1, which is negative 4, plus 4, which is 0. Now, why am I bringing this to place? This is because in mathematics, 0 is almost every case a very special number. And in this case, a dot product of 0 indicates that these two vectors, v and w, are perpendicular. In more precise terms, they're orthogonal, but you can think of them as perpendicular lines, like lines in a right triangle that have a degree of 90 degrees. That's how you can geometrically interpret a dot product. For perpendicular vectors, their dot product is always 0. Nice. So now, let me delete this and write a property for you to copy. Here you go. So, for perpendicular vectors, their dot products is equal to 0. Nice. I mean, you can think of an example, right? In our coordinate system, we have the unit vector I and the unit vector j. And because they are perpendicular, I dotted with j, which is the unit vector 1, 0 and 0, 1, is equal to 1 times 0 plus 0 times 1, which is 0 plus 0, which is 0. This is a very simple property we can memorize. And actually, dot products have lots of applications. For example, in physics, if you've talked about moments, we have a seesaw, and for example, let's put a weight of 4. I'm not going to specify the units because in mathematics we don't really care about them. And on the right side, we have a weight of 2. And suppose that this distance is negative 1 and this distance is 2. So according to the law of moments, they will be in equilibrium. So this seesaw won't tilt to any side. This is in equilibrium. Now, why is that? It's because on this side, 4 times negative 1 is 4. And on this side, 2 times 2 is 4. So because the number on the left-hand side is equal to the number on the right-hand side, they're equal. Now, we can also interpret this in terms of dot products. So let's call this weight 1, and this distance x1. And this is weight number 2 and x2. In this case, what we want is w1 x1 plus w2 x2 is equal to 0. So namely, we want their dot product to be 0. So this is how dot products can be used in physics. And also it can be used in economics and businesses. We can calculate the total income based on the dot product. If we have a vector of quantities like quantity 1, quantity 2, quantity 3, and a vector of prices, price 1, price 2, price 3, then notice that our total income, or the total you have paid, is actually equal to Q dotted with P. Because this is quantity 1 times price 1 plus quantity 2 plus price 2 plus quantity 3 times price 3. That's equal to the dot product. So in more general terms, v dotted with w is equal to the sum of its components. We don't have to worry about the size yet. Now, we're going to talk about lengths. A very important case is the dot product of a vector with itself. So consider dotting a vector v with itself. So v dotted with v. First of all, we have to recognize that this is basically saying that we're dotting all of the components to itself, which is the components squared. So this is the sum of all components squared. And this looks suspiciously like the Pythagorean theorem, and in fact it is. We can actually treat this as the length of the vector v squared. So if we have the dot product of 1, 2, 3 with itself, then that is equal to 1 plus 4 plus 9, which is 14, and this is equal to its length squared. So therefore, the actual length of the vector v is equal to the square root of 14. So the dot product isn't really about trying to solve for the length of something, but it tells you the relationship between the dot product and its length. And if you're also very unsure of why this is the case, in n dimensions, we use the n-dimensional Pythagorean theorem, which is basically a general case of the 2D Pythagorean theorem, which is a squared plus b squared plus c squared, all the way, that square rooted is the length. If you don't know this, then you should probably search this up, because this is a very important property if you're trying to deal with lengths and higher dimensional coordinates. Nice. So let's put this up here and star this. Now, knowing the relationship between the dot product and lengths, we can define a unit vector. A unit vector is a vector whose length equals to 1. Now, we can denote this very easily by u is equal to 1. Now, because we know that length has a relationship with the dot product, we can also say that u dotted with u is equal to 1, right? Because this is equal to the length squared. 1 squared is 1. So for example, in 4 dimensions, if we have the vector 1 half, 1 half, 1 half, and 1 half, then this has the length of a fourth plus a fourth plus a fourth plus a fourth, all over the square root, which is equal to the square root of 1, which is 1. And the dot product of this vector also gives us a fourth plus a fourth 4 times, which is equal to 1. So therefore, the dot product is equal to the length squared. Nice. Now, what we also want to do sometimes is we want to know what the unit vector for a particular non-unit vector is. And that means basically that we have a non-unit vector like, for example, 2, 2, 1. The length of v is the square root of 9, which is 3. But however, the length is not 1. But we want to construct a unit vector from this vector v. So how can we do that? We can basically do v over the length of v. And that gives us the unit vector of v. And we sometimes call this the directional vector of v, the direction of v. So why is this the case? Now, simply notice that when we compute the length of this vector, we can pull this out to the other side because this is a scalar. And so this is equal to 1 over the length of v times the length of v. Notice that we pulled this length term out. And therefore, this is equal to 1 because the denominator cancels out the numerator. And so this is why the direction of v, the vector divided by its length, is equal to a unit vector. Fantastic. So this is also an important property you might want to know, is that the directional vector of v is equal to a unit vector, which is v over the length of v. For example, a very special unit vector is u is equal to cosine theta sine theta. Its length is equal to cosine squared plus sine squared, which according to the trigonometric identity is equal to 1. Now, I will show you a very elegant proof of why the dot product of two vectors, of two perpendicular vectors, is equal to 0. Because we didn't really show that this is true. So now we're going to show it. For example, if we have two vectors, that are in right angles to each other. For example, this is V, this is W. With right angles, we can construct a right-angled triangle. Now, from the last lesson, we learned that this particular vector is actually V minus W. Or, in fact, the direction I'm pointing in is wrong. It's actually this, but the direction doesn't matter. All we have to know is this is a difference of the two vectors. And according to the Pythagorean theorem, because this is a right-angled triangle, we can denote the relationship as this. So this squared plus W squared is equal to the hypotenuse squared, which is V minus W. Nice. And let's write this in terms of the components. So we can write the length of V squared as V dot V, and the length of W squared as W dot W. And this is equal to V minus W dotted with V minus W. And writing out this in component form, we have V1 squared plus V2 squared plus W1 squared plus W2 squared is equal to V1 minus W1 squared plus V2 minus W2 squared. Now, if we expand this, expand the right-hand side, we have V1 squared minus 2V1 W1 plus W1 squared, and then plus V2 squared minus 2V2 W2 plus W2 squared. Over here, we can see that V1 cancels with this V1, V2 cancels with this V2, W2 cancels with this W2, and so does this W1. All we are left with is these two terms, which gives us negative 2 V1 W1 plus V2 W2 is equal to 0, because we have canceled all the terms on the left-hand side. And dividing this by negative 2 gives us V1 W1 plus V2 W2 is equal to 0. And we can extend this to n components, not just, well, 2 components. And now this is why the dot product of two perpendicular vectors is equal to 0. Now, there's also a very important property we have to get from the sign of a dot product. Suppose that V dot W is not 0. So suppose this case. So we know that it's not perpendicular. So it may be positive and it may be negative. The sign of V dot W immediately tells us whether we are below or above a right angle. So whether the angle between the two vectors is acute or obtuse. The angle is above 90 degrees when this is negative. So when this is negative, angle is above 90 degrees. And when V dot W is positive, the angle is below 90 degrees. Now, according to this observation, we can actually derive a trigonometric relationship of the dot product. So we can actually express dot products in terms of cosines. And let's start this definition with unit vectors. So we have a property of trig. And first consider two unit vectors, u and big U. U dotted with big U tells us whether the angle theta is less than 90 degrees or bigger than 90 degrees. Because the vectors have length 1, because we define them to be unit vectors, the dot product u dot u is the cosine of theta. So actually, u dotted with u is equal to the cosine of theta. Now, this only works if we have two unit vectors. And because the cosine of theta is between negative 1 and 1, we can say the absolute value of u dotted with big U is between 1. Remember that cosine of theta is never greater than 1, and it is never less than negative 1. And therefore, the dot product is actually between negative 1 and 1. The dot product is determined by cosine. Now, these vectors are presupposed to be unit vectors. How can we derive a relationship in which these are not unit vectors, but we can still relate dot products with the cosine? Okay, so suppose we have non-unit vectors, v and w. We have said previously that we can construct a unit vector from a normal non-unit vector. How can we do that? Well, we do that with the direction of v, which is v over its length, and the direction of w, which is w over its length. Now, these are unit vectors, so we can apply this property. So the direction of v dotted with the direction of w, this is equal to cosine theta. So theta is the angle between the two vectors. This is equal to v over the length of v dotted with w over the length of w. So this is equal to 1 over the two lengths multiplied together, and v dotted with w is equal to cosine theta. And fantastic. Now all we have to do is to multiply this on both sides, which gives us v dot w is equal to the length of v times the length of w cosine theta. That's it. So the dot product of two non-unit vectors is actually equal to their length times cosine. And if these are unit vectors, well, the length is equal to 1, and this is equal to 1, and 1 times 1 is 1, and 1 times cosine of theta is still cosine of theta, so everything still stands. And actually, this is a more general case, and this is more important than a unit vector case, because you can derive the unit vector case as a special case of this general case. Now, we can also notice an inequality over here. Cosine of theta is always going to be between 1 and negative 1, inclusive. This means that v dot w is between the maximum and the minimum. What is the maximum? Well, the maximum is when cosine of theta is the maximum, which is 1. So we have this when it's multiplied by 1. And what's the minimum of cosine theta? The minimum of cosine theta is negative 1, which yields this expression. All right. And we can more simply denote this inequality with an absolute value. So the absolute value of v dot w is less than or equal to the length of v times the length of w. This is called the Schwarz inequality. Very fancy name. I think it's called the Cauchy-Schwarz inequality, but I can't really remember that name, so let's call it the Schwarz inequality. Any more famous inequality can also be formulated in terms of linear algebra, and it's the triangle inequality. And it's saying that v plus w is less than v plus w. This is the triangle inequality. All it's saying is if we have two sides, then the sum of the two sides is always going to be greater or equal to the other side. All right, so this is the very famous triangle inequality formulated in terms of linear algebra. So these are very important properties you might want to research about. And now we can also use the dot product to prove why the arithmetic mean is greater or equal to the geometric mean. So we call this, I think, the AM-GM inequality, the arithmetic mean, geometric mean inequality. So let's consider the dot product of the following vectors. V is equal to AB, and W is equal to BA. So the dot product of V and W is equal to AB plus BA, which is 2AB. And the length of both V and W is the square root of A squared plus B squared. And now, from the Schwarz inequality, their lengths multiplied together is equal to A squared plus B squared. That is greater or equal to the dot product's absolute value. So that is greater or equal to 2AB, because their dot product is 2AB. Okay, so now what we can write is AB is smaller or equal to A squared plus B squared over 2. And if we substitute x is equal to A squared and y is equal to B squared, we achieve the famous AM-GM inequality. The square root of xy, which is AB, is less than or equal to x plus y over 2. And so AM, the arithmetic mean, is greater or equal to the geometric mean. For example, if we have A is equal to 2 and b is equal to 1, x is equal to 4, and y is equal to 1. This means the geometric mean, the square root of xy, is equal to 2, and the arithmetic mean, which is x plus y over 2, is 5 over 2, which is 2.5, and indeed 2.5 is greater or equal to 2. Nice. And basically that's it in this video. We talked about how we can relate dot product with cosines and lengths, and how we can also relate lengths with cosines. And we also recognized how the dot product of two perpendicular vectors is actually 0. So these are very important properties you might want to know, and hopefully you can get a grip of what these are. Thank you for watching this video.